Boolean functions. What is a Boolean function? A Boolean function is an expression formed with variables, binary variables, x and y, for example, operators, or and, parentheses, and equality sign. The result of the Boolean function is f has a binary value, 1 or 0. Okay. Let's take examples of some Boolean functions. f1 is equal to x, y, z bar. f2 is equal x or y bar z. f3 and f4. I can represent Boolean functions in a truth table. Notice that we have 3 variables in the functions. So the truth table will have these 3 variables, all the different possible inputs on the variables. Now f1 is represented as this. See, f1 is equal to 1 only if x is equal to 1, y equal to 1, and z is equal to 0. It is in this case here. x1, y1, z0. This is f1. All the other values of f1 are zeros. Now, can you find f2? f2 is equal to 1 if x is 1. All these cases, f1 is equal, f2 is equal to 1. And also if y is equal to 0 and z is equal to 1. And these are here. Now, f3 is equal to 1 if this term is equal to 1. And this is equal to 0, 0, 1. Or if this one is equal to 1, x equal to 0, y equal to 1, z equal to 1. Or in this case, if x equal to 1 and y equal to 0, regardless of the value of z. If I map this into the truth table, I will get this. If 4 is equal in the truth table to these values here. Now, from the truth table, you see that f3 is equal to f4. f3 is this. How do I know this? Look at the values 0, 0, 1, 1, 0, 0, and so on. So f3 is equal to f4. We can prove this algebraically by algebraic manipulation using the theorems that we have learned. Now this is f3. Notice that f3, I can take x bar and z, x bar and z out of these two terms, which leaves me with this. Here we have y bar, and here we have y. We know that y bar ORed with y is equal to 1. And anything you AND it with 1 is the thing. So what is left is f3 is equal to this ORed with this. Look at f3, it is equal to f4. Now, the complement of the function. If we are given a function f1 is equal to xyz bar, what is the complement of this function? The complement of this function. f1 bar is equal to xyz bar, which is this bar. Now, if we take the bar inside using the Morgans Theorem, we have x bar, and the AND here is converted to an OR, and then this is y bar, the AND here is converted to an OR, and then we have z bar bar. This is using the Morgans Theorem. And z bar bar is equal to z. In the truth table, this is f1 here. f1 is equal to 1 if x equal to 1, y equal to 1, z equal to 0. It is this case. Okay, if we try to map the complement of the function into the truth table, it is equal to 1 if x equal to 0. All these cases. Or if y equal to 0. Here and here. Or if z equal to 1, which is this, 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 and this. And if we apply this, we come up with this function. This is f1 complement. You notice that we get f1 complement by complementing every output here. The 0 becomes a 1, 0 becomes a 1, and the 1 becomes a 0. So given a function f, the complement of this function, which is f bar, is obtained by interchanging the 1s with 0s in the function's output values. In general, we use the Morgans theorem to obtain the complement. If we have a function like this, what is the complement of this function? It is a bar ANDed with this OR is converted into an AND. B bar, C bar, and so on. If the function given as this, the complement of the function will be A bar or B bar or C bar, and so on. Now let's look at some definitions. What is a literal? A literal is a variable on its own or in its complement form. For example, x is a literal, x bar is a literal, y is a literal, y bar is a literal. So a literal is a variable, whether it's complemented or uncomplemented. What is a product term? It's a single literal or the AND of several literals. For example, this here is a product term. Why? Because it's a single literal. This here is a product term. Why? Because it's the AND between several literals. This here is a product term because it is the AND of two literals. This is the AND of two literals. So these are examples of product terms. A sum term is a single literal or the OR of several literals, the logical sum of several literals. For example, this here can be considered as a sum term. Notice that here can be considered as a product term. Here, the same term is considered as a sum term because of the definition. Now, this here is a sum term. Why? Because it consists of the sum of literals. This one is a sum term. This one is a sum term. We prefer some forms for the expressions, desirable forms of Boolean expressions. Certain types of Boolean expressions are desirable. Why? From the implementation point of view, and we will see that later. Namely, if we have the form sum of products, we put the function in this form, sum of products form, or in product of sum forms. These are called standard forms. Okay, let's see what is sum of product form. Let's take example. F is equal to x. This here, this function is put into the sum of product. Why? Because it consists of a product term or the ORing of several product terms. F here is in the standard form sum of product because this is a term, a product term, x, and this is a product term and the sum of these two terms. Here also this is a term, a product term, and this is a product term, and we have the sum of these two terms. So we say that this function is in the standard sum of product. This is another example. This is a product term and this is a product term, and the sum between them. So this function f is put into the standard sum of product. In the product of sums, this function is the and between sum terms. This is a sum term, as we saw before, and this is a sum term. The product of these two will put the function in the standard product of sum. In this example, this is a sum product, and this is a sum product, and the and between them will give the function in the standard product of sum form. Also, this is in this form, the standard sum of product, because this is a sum and this is a sum and the and between them. Also, this function is the f equal to x, or can be said to be in the product of sum form. Why? Because we can also consider this as a sum term, because a sum term is defined as a sum term or an and of several terms. Now, it's nice to have the function in the standard form, or either in the sum of product or in the product of sum forms, because it's easier to implement. Now, this function is in what form? This is in the standard sum of product. It is a product, it's a product, it's a product, and we have the sum between them. So it is in the standard sum of product. This function is in the standard product of sums. Product of sums. This is a sum, and this is a sum term, and this is a sum term, and we have the product between them. So this is in the product of sum. How about this function? This function actually can be considered as a product of sum or sum of product. Sum of products, if we consider this as a product term, and this is a product term, and this is a product term, and we have the sum between them. If we look at this as one term, then it's a sum term. That's why we said this is it can be in the sum of product or in the product of sum. The same applies for this function. This can be considered as one product term, or it can be considered as the product of these three sum terms, x, y, and z bar. How about this one? Actually, this one is not in the standard form. This is not in the standard form. And the same for this function. It is not in the standard form. It's not in the product sum or product SOP or POS. How do we implement these functions? Look at the functions here which are put in the standard forms. They are easy to implement. Here, for example, if I want to implement this function, f equal to x bar y, and so on, I can put this one on an AND gate and put this term on an AND gate and this one on an AND gate, and then put an OR gate that takes all these together. Here I can have an OR gate for this term and an OR gate for this term and an OR gate for this term, and put the outputs of these three OR gates into an AND gate. The same goes here. However, if it's not in the standard form, it is a little bit difficult to implement this function. I need an AND gate here, an inverter for this one. The output of these two gates is put into an OR gate, and then the output of this whole OR gate is put on an AND gate with X. And this is also more difficult. That's why we put the functions in the standard form.